Now we're going into chapter 2. So this is summarizing and graphing data. For an outline of chapter 2, we're starting with 2.1. And this is frequency distributions for organizing and summarizing data. And the student outline that you have is going to cover 2.1 and 2.2. So you'll be able to complete that entire packet after watching both this lecture and then the next lecture. Okay, a key concept for 2.1. So when working with large data sets, a frequency distribution or a frequency table is often helpful in organizing and summarizing data. And you'll see what these look like on the next slide. So frequency distributions help us understand the nature of the distribution of a data set. And in statistics, we think about a distribution as the possible values for a study and how often they occur. Okay, so here's an example of a frequency distribution table. It shows how data are partitioned or grouped among several categories or classes. In our example, those categories are the time in seconds for drive-through service times. We do this by listing the categories along with the number or the frequency here of data values in each category or class. And we'll talk about how to make these frequency distribution tables, and you'll get practice doing this. Some really critical definitions in 2.1 related to frequency distribution tables are the lower class limits. So this is the smallest numbers that can belong to each of the different classes. Okay, for example here, our lower class limits are 75, 125, 175, 225, and 275. And then for our upper class limits, this is the largest numbers that can belong to each of the different classes. In this example here, our upper limits are 124, 174, 224, 274, and 324. The next definition here is class boundaries. So these are numbers that are used to separate the classes, not using these gaps that we just established for the lower and upper class limits. So we're not using the gaps created by these class limits. Instead, how to figure out the class boundaries is we subtract 0.5 from the lower limits and we add 0.5 to the upper limits. So for example, with our table here, these class boundaries are 74.5 because we subtracted 0.5 from that lower class limit. The next class boundary we have is 124.5. So we added 0.5 to the upper limits to get 124.5, but we subtracted 0.5 from 125 to get that class boundary of 124.5. Okay, so these class boundaries, you're either adding or subtracting 0.5. So we end up with 74.5, 124.5, 174.5, because that falls in the middle of these two classes, and so on and so forth. So in the previous example, we looked at the upper and lower class limits were whole numbers. So to find the class boundary, we could just add and subtract 0.5 to each of the lower and upper class limits. Here, however, we have upper and lower class limits that are decimal places. So we go out to the hundredths place. So we couldn't add 0.5 and subtract 0.5 here. That would not give us our class boundary. Instead, to find the actual class boundary values, which are defined as the halfway point between a lower class limit and an upper class limit, here instead of adding and subtracting 0.5, we need to add and subtract 0.005. And we figure that out by averaging 1.74 and 1.75 to find the midpoint. Then to get that midpoint, we can see that we would need to add 0.005 to 1.74. The next example we can look at is starting at 0 for that lower class limit. To get the class boundary associated there, we would subtract now 0.005. Okay, so it's really the midpoint between the upper and lower class limits. Sometimes you'll add and subtract 0.5. Sometimes you might need to subtract a different value to find those class boundaries. And to clarify one point before we go to the next slide, remember these class boundaries, we're looking at the halfway point between the upper class limit of one class or category or one row here, and then we're looking at the midpoint between that and then the lower class limit of the next row down. So we're looking in between classes and categories. Where you'll see for the next definition we get into, we're focused on the midpoint just within one category or class. Okay, additional definitions here for these frequency distribution tables are class midpoints and the class width. Class midpoints, they're the values in the middle of the classes. Each class is a midpoint that can be found by adding the lower class limit to the upper class limit and dividing the sum by 2.
Essentially, we're taking the average of 75 and 124. So to take the average, we would add 75 and 124 and divide that sum by 2 to get 99.5 as one of our class midpoints.
I want you to practice doing these for the other classes and check your answers in the textbook. Next, we have class width. So the difference between the two consecutive lower class limits in a frequency distribution. So for example, we have 75 as one lower class limit. We have 125 as our other lower class limit. The difference between 75 and 125 is 50. And we should have the same class width if we took any of these classes into account. So practice doing that. Take 275 minus 225, take 225 minus 175, and confirm to yourself that we still get 50 as our class width for this example. Okay, you're going to practice doing a frequency distribution table. We're also going to talk through this one together. Step 1, select the number of classes, usually between 5 and 20. How many classes are in the McDonald's example? Well, we have 1, 2, 3, 4, 5 different classes. Step 2, calculate the class width. Okay, so that is approximately equal to, so that squiggly equal sign means approximately equal to. Okay, so it's approximately equal to the maximum data value minus the minimum data value divided by the number of classes. In our example here, we have 5 classes. And the main rule for picking the number of classes is to stay between 5 and 20. Now we would take the class width that we calculated and round this to get a convenient number, a whole number, and it's usually best to round up so we can be more inclusive with the data set that we have. Okay, here on this slide, I've summarized all of our main definitions for this example. So lower class limits, upper class limits, our class boundaries, our class midpoints, and our class width. Okay, so the lower class limits we see here, 75, 125, etc. Upper class limits we see 124, 174, 224, etc. The class boundaries, remember we either added or subtracted 0.5 to our lower and upper class limits to get our values for our class boundaries. Class midpoints, that's where we took the lower class limit plus the upper class limit and divided by 2. Essentially, we took the average of that category's lower and upper class limit. So for the class width, going back to this slide, we calculate that by taking the maximum data value minus the minimum data value and dividing by the number of classes, and then rounding that up to a whole number. To check that on this frequency distribution table, we could also look here and say that 125 minus 75, that's also equal to our class width. And we will get into an example where we calculate the class width when you see all the data in front of you. But this is one way to check that we do have the correct class width here. So 125 minus 75 is equal to 50. And again, we'll do an example with a full data set. Step 3, choose the value for the first lower class limit by using either the minimum value or a convenient value below the minimum. So here we would presume that if we see 75 is our first lower class limit, then that is either equal to the minimum value in the set of data, or it's a convenient value that's below the minimum value. And again, we'll go through and actually look at the full data set after we talk through these steps. Step 4, using the first lower class limit and the class width, list the other lower class limits. Okay, so we would take our first lower class limit that we decided on in step 3. We add the class width, which is 50. Now we should see that the next lower class limit here is 50 greater than our first lower class limit. Again, we'll go through an example of this. Step 5, list the lower class limits in a vertical column, so 75, 125, 175, 225, and 275, and then determine and enter in the upper class limits. So how do we do that? Well, we decided on these lower class limits. To get the upper class limits here, we want to take the second lower class limit, so 125, and subtract 1, and we get 124. Okay, so our first upper class limit is 124. You'll see the same thing has happened for the rest of the table. So 175 minus 1 equals 174. 225 minus 1 equals 224. 275 minus 1 equals 274. Step 6, take each individual data value and put a tally mark in the appropriate class, and then add the tally marks to get their frequency. So we'll practice doing that once we have our full set of data. But these frequencies represent each individual data point. And for example, there were 11 data points that fit into that time range of 75 to 124 seconds. So now let's actually practice all of this. We've talked through the steps. Here we have the full data set that we need in order to construct this frequency distribution table. So now we can actually practice the steps, look at our full data range, and make a table like this on our own. Okay, step 1, we're going to select 5 as the number of desired classes. Again, the only real rule here is to stay between about 5 and 20 classes. You don't have so many classes that the data table becomes really complicated. You also don't want to have too few of classes where you're lumping in 75 seconds up to 3 hours, for example. So you want to select your classes so that your data makes sense that you separate it into 1, 2, 3, 4, or 5 classes, for example. So you really have to look at the data set that you're working with. Step 2, calculate the class width as shown below. So we need the maximum data value, we need the minimum data value. We know our number of classes here, we selected 5. So now we'll go back to this data table and find the maximum value and the minimum value. So pause this, make sure you identify the maximum and the minimum value. So you should have spotted 308 as our maximum value and 83 as our minimum value. Going back here to step 2, we plug in the value for our maximum data value, our minimum data value. The number of classes is 5. We end up with 45, so we're going to round that up to 50 to make it a more convenient number to work with. And that is how we figured out we wanted a class width of 50. Step 3, the minimum data value is 83. We just looked at the table and found that, which is not a very convenient starting point to work with. So we're going to go with a value below 83 as our first lower class limit. So a convenient value to work with here would be 75 as our first lower class limit. Step 4, add the class width of 50 to the starting value of 75 to get the second lower class limit of 125. Continue to add the class width of 50 until we have our 5 lower class limits. Okay, so we start out with 75 as our first lower class limit because it's below the lowest value of 83. And we didn't want to work with 83. It's not that convenient of a number. We already calculated our class width. Now we're going to add 50 to get 125. And we'll continue to add 50, which is our class width, to each of these lower limits to get the next one. Step 5, list the lower class limits vertically as shown to the right. So we've done that here. We have 75, 125, 175, 225, and 275. This dash here represents that we're going to have a range of values, so 75 to some upper class limit, but we haven't decided on those quite yet. Okay, from this list, we will end up identifying our corresponding upper class limits. Remember how we talked about doing that? We take the second lower class limit, we subtract 1, and we end up with our first upper class limit. So I want you to fill these in and then check your answer. Okay, so this is what you should have gotten. So we have this value minus 1 equals 124. This lower limit minus 1 equals 174. And again, so on and so forth. So we end up making our lower class limits and then our upper class limits we would list here. So I've written in our upper class limits here. One I want to talk about specifically is how did we get 324 if we don't have anything to go based off of? So we wanted to take 275 plus the class width of 50. So 325 would be our next lower class limit, but we don't have any data that falls into that class or that category. So we will go ahead and do that calculation though. Take 325, subtract 1, and we end up with this as our upper class limit for that last category. Step 6, enter a tally mark for each data value in the appropriate class. Remember, we just created these classes, so 75 to 124, 125 to 174, etc. we end up looking at this full data set and we pick which class that data point falls into and we tally that up. Okay, so we would take, for example, 107, that would fit into this first class. So I added a tally here. You would want more room to do this, but you would go through each data point individually and sort each data point into the class that it belongs in. 139, we go back here, that's gonna fall into this class. So I'm adding one tally mark there, and we keep going with every single data point that we have. So I want you to practice doing this and then look at the answer on the next slide. You've done this now, you looked at 107, 139, 197. You've decided what class each of those data points belongs to, and you've tallied up that we have 11 data points that belong in the category of 75 to 124 seconds. Similarly, we have 24 of these data points that fall into this category of 125 to 174. Okay, so that's how we would make a frequency distribution table. You do have another example to practice with on page 1 of your student outline. Another concept here in chapter 2, section 1 are relative frequency distributions. So for these, each class frequency can be replaced by a relative frequency or a proportion or a percentage. So here's our relative frequency equation. Here is our percentage equation. So for the relative frequency equation, we take a frequency for a specific class, and then we divide that by the sum of all the frequencies. We'll do an example. For the percentage for a class, we have the same thing, the frequency for a class divided by the sum of all frequencies times 100 to get the value into a percentage. Okay, the sum of the percentages in a relative frequency distribution must be very close to 100%, like we talked about previously, and there can be some wiggle room for rounding errors. Okay, so let's do this example. One thing we'll need is a frequency for a class and the sum of all the frequencies. So if you add these up, you should get 50. I want you to practice doing this on your own too. And then let's go ahead and pick 11 as our frequency for one of the classes. So we have 11 divided by 50. And you should calculate that to be equal to 0.22. This is our relative frequency for the class 75 to 124 seconds. Okay, let's now do an example for percentage. So for percentage, we have the same part of the equation. So again, we'll take 11 over 50, that equals 0.22. To get this value into a percentage, we're gonna take 0.22 and multiply it by 100%. So to do that, we would move the decimal point over 2 places. We end up with 22%. So you should practice doing this for our other categories / classes. So we just did the class 75 to 124 seconds. You can repeat this for each of the classes that are in this table. And remember one really important part, if you do that, then you should get a number very close to 100% once you add up all of these individual percentages for each class or category. Okay, so next up we have a cumulative frequency distribution. This is when we have the frequency for each class is the sum of the frequencies for that class and all the previous classes. Okay, so what do I mean by that? If we have 11, then that's the sum for this one class. If now we're looking at 24, we would take this value plus 11 to get the next cumulative frequency. And I want you to practice this and then check your answers, which are provided in the student outline document. If we were looking at this category, we would take 10 plus 24 plus 11 to get the next cumulative frequency. Okay, so definitely practice this on your own and check your answers in that student outline document. Okay, so next we have using frequency distributions to actually understand our data. So again, in statistics, we always want to think critically about our data and what sort of conclusions we can make based on that data. So in statistics, we are often interested in determining whether the data have a, quote, normal distribution. What does this mean? There's 2 rules to determining if we have a normal distribution. One is that the frequencies start low. Okay, so they're starting low, then they increase to 1 or 2 high frequencies, then they decrease to another low frequency. Okay, so that's rule number 1. Rule number 2 is that the distribution is approximately symmetric, where frequencies preceding the maximum frequency should be roughly a mirror image of those that follow the maximum frequency. So what would we look for in a graph like this is we could draw this proposed line of symmetry and see that if indeed we reach a high frequency point, then we drop back to lower frequencies. This is sort of a simplified example because we essentially see perfect symmetry, right? It goes up, we have our line of symmetry, and this data point exactly mirrors this data point. This data point exactly mirrors this data point. Okay, so these are the rules we use to determine if our data do have a normal distribution. Next, we're going to talk about gaps and comparisons. So gaps can show that the data are from 2 or more different populations. So for example, in all of these graphs, we have a gap here. This could mean that this is one population and this is a different population. Again, this is one population and this could be a different population. However, we cannot make the conclusion that the converse is always true. The converse being that 2 or more different populations always result in gaps. Even if we do have 2 different populations present in our data, that won't necessarily lead to a gap in our data. And also something to note, these graphs here are a sneak preview of Chapter 2, Section 2, where we'll look at histograms. An example here of gaps is this set of data. So here we have the weight in grams of pennies, and we have their frequencies. So remember, what does that frequency mean again? We measured the mass of all of these pennies, and 18 of those pennies fit into this category of being between 2.40 and 2.49 grams. And there is a clear gap here in our data. When we're looking at this table, we do see a large gap between the lightest pennies and the heavier pennies. This suggests that we could have 2 different populations of pennies present in our sample. And this could actually be very well true because pennies made before 1983 are a different composition of metals. So they had more copper than zinc. And then after 1983, due to restrictions on materials, we have less copper present in those pennies. Okay, so we see a gap here. This indicates that we could have 2 different populations present in that set of data. But remember our caveat here. So just because we have 2 populations in our set of data, that doesn't always result in a gap. But in this case, we do see a gap and we have background knowledge to know that maybe we do actually have 2 different populations in that data set. Okay, so next we have comparisons. So sometimes combining 2 or more relative frequency distributions into one table makes comparisons of that data much easier. So for example, we have time in seconds on the left, we have McDonald's frequencies, and we have Dunkin' Donuts frequencies. So we put both of their relative frequency distributions into one table so we can more easily compare. So again, an example of critically thinking here is we should probably consider the types of menu items that each fast food establishment offers. And because their menus are very different, we would expect the times to be pretty different for how long it takes a customer to go through a drive-through. And because we put the frequency distributions into the same table, now we can more easily compare, and we do see that Dunkin' Donuts service times appear to be lower overall compared to those of McDonald's. Okay, so that is the end of 2.1. After watching this, you should be able to complete the first half of the example on page 1 of your student outline. And from chapter 2, section 1, you should get through pages 2, 3, and 4 on your student outline, in addition to being able to answer the first half of the example on the first page. I want to cover this one problem in your chapter 2.1 homework. It's problem number 8. So this problem in particular, it involves a variation on determining class widths and lower and upper class limits. So for example, let's go into it. For problem 2.1.13, this should be problem 8 in your 2.1 homework assignment. Let's say we have a lower class limit of 2.720 inches and a class width of 0.010 inches. Now, to find the lower class limits, we'll take our first one that's given to us, 2.720. We add the class width here of 0.010. We get our second lower class limit of 2.730. Then to find the next lower class limit, we would take 2.730, again add our class width, and we end up with the next lower class limit of 2.740. One tricky thing here, to find the upper class limits, we need to select values that span between the lower class limits, but the upper class limit cannot overlap the lower class limit values. So let's talk about this one. Let's say we have our lower class limit of 2.720. The next lower class limit is 2.730. So we need to select an upper class limit that spans between these lower class limits, but it doesn't overlap either of these lower class limits. So to accomplish this, the best value we can pick for that upper class limit would be 2.729, right? Because it goes from this lower class limit, it goes right up to this limit, but it doesn't overlap either one of those. Okay, so that's how you would select these upper class limits when you're given class widths that are very, very small and even less than 1. So this is how you would approach problems like this. So like problem 8 on your 2.1 homework. Now, if you need additional help with this problem or problems like it, please always reach out to me through email or during office hours. Okay, so that is the end of chapter 2, section 1. I hope your first weeks went really well, and always keep me posted with any questions that you have. Okay, talk to you all very soon.